Hello and welcome to the next lesson. We're looking at friction, the rest of the story. When you have forces at angles, it's going to change your normal force and you have to calculate that first. So it's the only extra bit. But before we get to that, I want to show you a couple things. The one that I found recently here, a nice little video that relates to our gravity is not real discussion.
Water is spraying out of the holes because gravity is pulling on the water, right? But if Einstein is right, if I drop this bottle, the water will no longer feel gravity, so the water should stop spraying out. So let's see it. 3, 2, 1. Whoa. Wow. Come on now, okay.
So as soon as the bottle's dropped, then it's in an inertial reference frame, right? It's freely falling towards the earth, not feeling a force, not feeling it's accelerating, and so on. The water just it doesn't get pushed out anymore by gravity. It's freely giving in to gravity. So neat one. So I'm going to show and talk about how this equation for friction that you got used to in the last lesson really is true, and talk about what it means, like some implications of it that I didn't mention before on purpose. I just wanted you to get used to using it. Yeah, and then we'll finally get to the angles, and we'll also talk about why this is hard to believe, I should say, actually, before we get to that. And then we'll get to forces at angles. So here we go. So having worked with this equation, we know that friction only depends on what? Well, it depends on the normal force, which depends on the mass or the force of gravity, and also the types of materials, right? So that's it. That's all there is. Just that's all it depends on. So, it's just the normal force, contact force, and then it's basically the same as the normal force, but then the coefficient of friction gives you the sort of the percentage of it that it is, right? And so a lot of people have trouble believing that the surface area isn't a factor. And so most would think that it would matter. People with, most would think it matters. Just as I don't know if this means much or not, but if you notice that people with big feet and small feet aren't more likely to slip and fall, with rubber shoes on concrete, at least anyways, that would be supporting observation that surface area doesn't matter. But the problem is there's lots of situations where surface area clearly does matter, but it is different situations. So we need to identify that so that you're not thinking that surface area doesn't matter, kind of, sort of, but only in a physics class. It really doesn't matter, but for a specific situation. This is a demonstration that I've done. I don't have the video of it, but like this friction block here has a surface area of 2 units, 2 rectangles, and then on this side over here, it only has an area of 1. And when you put some blocks on top of it and then see what force it takes to get it going, you see there was a static friction and then a kinetic friction each time, give or take, right? So around 3 newtons, give or take, for the static, and 2.5 for the kinetic, just like before. And then, the green here. The red graph is from when it was 2 square units, 2 units hitting or dragging on the table, and the green was when it was on edge with only the one surface area unit on there. And so it was the same force needed. It didn't matter what amount of surface area was contacting. Okay, so clearly surface area is not a factor with quote unquote friction. And that's why I'm putting the quotes there, because we're going to talk about other cases soon. But it's difficult to believe because there's life experiences what's called traction, where surface area is a factor, and we'll get to that soon. Just before that, though, let's analyze a little bit further how this can even make sense. Where we're talking about friction, being from there's no surface area damage. We just have the object sliding in contact. We have forces due to the interactions of electromagnetic fields, right? That we've talked about. So the friction results are undeniable. But the question is, why do they exist, right? Why is it true? And so this video is pretty awesome to show why. Just have to hit refresh, maybe. There we go.
Leonardo da Vinci thought a lot about friction. In his studies, he determined that blocks of the same material and mass experience the same frictional force, regardless of the shape or orientation of the blocks. The size of the apparent area of contact doesn't affect the friction, which seems counter to what we experience.
Anybody wondering why it says apparent area of contact? It comes into play later on. But this, the discovery was that they just accelerate at the same rate. The amount of friction doesn't change, and for quite a while, people wondered why. And this video talks about it.
To understand why, we need to zoom in on the surface texture. At this level, the block is not resting on all of the points of the surface, only a small amount of peak material. When the block is set on a hard surface, the highest peak makes contact and tries to resist the load. Most likely, the load is too great, and the peak crushes or plastically deforms. More peaks resist the load.
So again, it's not getting damaged, it's just getting squished, right?
Load and crush, further and further until the load is supported. The area of material that supports the load is called the real area of contact.
Even though the block is a certain number of square centimeters, the real area of contact is really just those tips of the textured or bumpy shape that touch first and squish and then support the load. So picture them as little springs, right? If you had short springs and long springs, you might end up just loaded. The load would be supported by the longest springs that compressed first. The other ones wouldn't be touching at all.
It's typically a very small percentage of the apparent area of contact. For this 12-inch steel cube, the real area of contact is only about 0.01 inches squared. The amount of friction depends on the real area of contact, and for this case, where the surface deforms plastically, the real area of contact only depends on the material hardness and the force pushing down.
In other words, UFN, right? The material hardness is going to contribute to that mu value, and the Fn is just how hard the force of gravity is pushing down on it, right?
The apparent area of contact does not affect the friction at all. However the block is oriented, the amount of...
So those dots there add up to a certain amount of area of squish of the material to support the weight.
Block is oriented, so the amount of peak material making contact remains the same.
Same dots.
Though it may be distributed differently. Da Vinci observed this fact about friction, but it took modern measurement techniques and microscopes to explain what's really happening. Michigan metrology.
So it's like something that's actually been measured, which is pretty cool. All right, so we have a little bit more reason as to why here, right? But the idea that there's a real area of contact. That real area of contact really only depends on the material hardness, the flexibility of it, the properties of it, right? Overall, and yeah, the force pushing down. Okay, so this is hard to believe. And this one here too, by the way, the electromagnetic interactions, of course, are going to depend only on the real area of contact, right? So it all contributes to that FF equals mu Fn. But the more common situation where there is surface damage is traction. And so because this is observed and basically experienced all the time, it's why it's the results to do with friction only depending on the coefficient and normal force, not depending on surface area, is hard to believe, right? So some good pictures here that help you think about traction. You've got the lugs of this bulldozer's track digging into the sand and like physically, crushing the material. And if it started to spin, it would be shooting material backwards the other way if you're spinning your tires or whatever. And you got like Newton's third law kicking in to push you forward and so on, right? It's a very, very different situation. Okay, so when I think objects dig in, surface area certainly does matter because you're going to be grabbing more of the surface and more of the ground and so on. Jeepers, I'm one of those people. We air down our tires, which does a lot of things. One of the things it does is it increases the contact area. It actually just sort of lengthens it. It doesn't really widen it a whole lot, but it makes the tires perform or act a little bit more like tracks, grabbing more of the ground, giving you more traction. Okay. It also makes the ride smoother and makes it less likely to damage your tires and makes it less bumpy and whatever, right? But Oh, it makes it less likely to damage the trail too, so tread lightly. Anyways, other reasons. So this is certainly a big contributing factor. Another one that students will point to is like, well, what about the super wide tires on dragsters? Isn't that to get more, more friction? You think it would be kind of a friction situation, and it is, but the width isn't giving you the extra friction. It's actually that they're able to get them super soft and sticky. Okay, so first of all, we have to recognize the concept of pressure. So let's say there's 100 Newton force pushing down. If we had only 1 square meter of contact, the pressure would need to be 100, newtons per square meter, or whatever that equivalent is in PSI, pounds per square inch. If we have 100 newtons on a 4 meter squared surface area, then the pressure would only need to be 25 newtons per square meter. Okay, so these can have much lower pressure in them because they have more surface area contacting. Okay, you know this from mountain bike tires versus like street road bike tires. The tiny little road bike tires, if you've ever inflated one, have like 180 psi or something in them, whereas mountain bike tires have they're happy with like 40 to 50, maybe 60, I think is the max of them, right? So you don't need as much tire pressure for the big wide fat bike tires. I'm guessing they're probably like 20 psi or something. I don't know. I haven't experienced one yet. So how it relates to dragster tires is they're able to do the big burnout and get the tires all hot and sticky and really soft, and they need the pressure to be low so that they don't explode, right? Being so soft. So that is the information to do with that that pertains to this. So hopefully that helps you recognize, that this traction kind of situations, traction situations are the big reason why it seems weird to smart, observant human beings that, think that surface area should be a factor, but it's not. All right, so friction, we got our mu(f)(n)s, and then applied forces at angles, we know that changes the normal force. And so you're going to need to deal with that, right? We know that having a pulling force upwards reduces your normal force, and having a pushing force downwards increases the normal force. So we just need to remember to do that in context of these friction questions. So if you have, a gravity force of 10, and we have this applied force of 3 newtons at 30 degrees, we're going to often know that the acceleration in the y direction is 0. And so the net force in the y direction is 0, and the net force is all the forces added up. This is old news, right? Previous lesson, like lesson 59 or something. So we have a gravity force, an applied force, and a normal force all in the y direction. And so the way it works out, of course, is your normal force isn't 10 in this case. It ends up only being 7. Okay? So smaller normal force, therefore less friction, and so on. Okay, so it's a factor. We gotta factor that in. So here we go. This is a similar question. So we've got a 10 kilogram mass with a kinetic coefficient of friction of 0.3 on a level surface for now. We have an applied force of 50 newtons, pulling force, I guess, at 20 newtons above the horizontal. Could be pushing from an angle below, I guess, too. And so we're going to determine the acceleration, right? And so if you're just asked for the acceleration, you just have to go ahead and do all the work. You'd probably be a good idea. It would probably be a good idea to draw a free body diagram to get an idea of all the forces. Calculate your normal force, calculate the friction force, and all these steps to get the job done, right? So what that would look like, I don't have reveal blocks on this one, but we have our gravity force down at the 98. We've got our pull at an angle. We're visualizing a normal force and a friction force, and so on. We can adjust the sizes of those later if needed, right? Knowing the acceleration in the y direction is 0, we know our net force is 0. We've got our gravity. We've got our applied force component upwards, right? And solve for the normal force. And then get the friction force. And then finally, acceleration in the x direction is just the net force of all those x direction forces. We have the applied force sideways, and we have the friction force backwards, right? And so this FA X is in red there, and then we'll make that one be green to match the green writing there for the calculation to do with it. There we go. Some more greens. Yeah, and so we end up with a net force we calculate, and then of course an acceleration. So most of this is old news. We're just putting it all together. It's all old news, really, right? We've covered friction calculations. We've covered new normal force calculations. We're just putting the two together, right? What do we have here? 10 kilogram block force. Oh, so if we have a friction force of 8 newtons, determine the applied force to the right. If it was a horizontal force, determine the coefficient of friction, determine the applied force if it was at an angle of 42 to the horizontal, determine the coefficient it would have been in that case. Like there's different versions that you could go through with this, right? So go through those. So if the applied force, what do we have here? So the friction is 3, sorry, the acceleration is 3. So we know there's a net force of 30 newtons. And so that means that we know that we have an applied force of 30 newtons sideways, right? So we'd say, okay, sorry, net force of 30, and it works out to be an applied force of 38, I meant to say, right? So that's just calculating the applied force. The friction coefficient, obviously we know the gravity force is just the normal force in this case because it's a sideways force. So we can just plug in the known values and divide out and solve for the friction coefficient. If we have the force at an angle, so we have to do some work to look at that force at an angle, right? So if we have a force at an angle, we still know the net force is 30, and we still have this net force of 38 and so on. But that 38 would actually be the x component of the applied force, right? And so you can work backwards and say, okay, well, then the applied force, we know the component is always this size of the force times the sine or cos of the angle, cosine in this case, because we're adjacent to it. We can actually solve out for what the applied force would have had to have been. In this case, we have an applied force of 51.1 newtons. Making this all happen. And then the final case here, if we said, okay, well, if we have this 51.1 newtons applied at an angle, and we've got a vertical component of that applied force up, we've got the normal force that we are going to solve for. We have that gravity force, right? So we're basically solving for that new normal force, right? So we have that new normal force that's reduced by that component of the applied force, and yeah, so we end up with a different normal force and therefore a different coefficient of friction. So this question is a little bit weird. Like it's not like, oh, now we're going to apply a force upwards at an angle. It's actually a new situation, and it results in that same. We need a different material to result in the same acceleration with that same force, of course, right? Or that when you're pulling at an angle, I should say. Yeah, hope that makes sense. And don't forget, there's questions where you can be pushing down as well. So that's in this one here, in number 3, the force is below the horizontal. Yeah, so this is that to do with that video and the idea, or well, just the idea that surface area doesn't matter. This one, you're pulling above the horizontal, and I've got the steps in there to help you out. But obviously, we could just ask, like, what's the horizontal acceleration, right? And so these steps probably be good for you to do as a way to carry yourself through the question. And then just modify the value at the end here. Like, what if the force is only 2 newtons? What would that cause? And what I'm hoping for you to notice here is that you're going to be pushing at less than the friction force. And hopefully you're not going to conclude that means that it accelerates towards you, like we've talked about in the past. All right. So that is it for that. If you have any questions. As always, thank you for watching.